Hi, my name is Owen Casas, and this video is a brief explanation of a project that I did constructing a fictitious wind farm on top of Ragged Mountain. So what I'm not going to do in this video is go into depth on each slide that is in the PowerPoint that you have access to on the website. You can do that on your own time and evaluate my numbers a little more thoroughly. But I am going to go over every slide and briefly talk about them and just to do a basic overview of the project, the methodology, some of the numbers behind it, and a summary. So starting is the scope of the project, where and what I was doing. So I constructed a fictitious wind farm on top of Ragged Mountain, which is in the Mid-Coast, Maine area overlooking Penobscot Bay. The farm consisted of a road that was approximately 1.16 miles long going up the side of Ragged Mountain, factored in cutbacks as well for the steepness of the mountain. And along the top and the ridge would be 4 Vestas V90 wind turbines. So that's discussed on the first slide. The second slide, I briefly talk about the methodology that I used and have a caveat in there. My methodology was professional estimates and summaries on certain aspects of the turbine components, breaking them down into lump materials that I could equate to British thermal units. So I equated everything down into a common unit of energy for ease of finding energy equilibrium. The caveat is that this is a very large project, and doing it properly and comprehensively is beyond what I could do with my resources and the time that I had. But I did do as good a job as I could and equated energy to the largest components of this. Gives you a really good baseline when thinking about and assessing a project of this scope. So factors that I did not use were the smaller things that require a lot more in-depth knowledge. Vestas, which is the turbine manufacturer that I used, has done many projects of this scope, and they factor in a lot of different things. Recycling after the fact, maintenance of the turbines themselves during the useful life of them, and all the fluids that are in it, small electrical components. I did a rough estimate of everything, but tried to be as comprehensive as I could. The wind speeds that we used were taken from a University of Massachusetts Amherst study that was done up on top of Ragged Mountain utilizing one of the communications towers up there. They correlated buoy wind speeds from Penobscot Bay and 30-meter height wind speeds actually taken on Ragged Mountain to do an extrapolation of what projected wind speeds would be at 80 meters, which was the hub height that I chose. So that's where I got the wind speeds that I used in the algorithm, in the formula for determining energy output. So this is a brief view of the actual site. This is Ragged Mountain, looking at it from the Mirror Lake side. Once again, I just cover real quick what the scope of the project is. On this slide there's useful information that I used in my mathematical summation of energy used and energy consumed balanced against the energy output. So useful things, British thermal units, how many BTUs are used in a ton of steel, equating BTUs for the materials used in construction of these turbines. In this slide I talk about the energy intensity of producing one V90 wind turbine, and then you can see that I have times that by 4 for the amount of turbines actually that would be in the wind farm itself. One of the large energy consumption factors is the foundation of the turbines itself, so you don't want to leave that out. Concrete and rebar used in the foundation of it. Another large consumer is the copper wire needed to actually connect the wind farm to an existing power grid. So having your farm in close proximity to a power grid definitely reduces energy consumption. Transportation to the site and consumption at the site. I went from where the turbines were actually manufactured by Vestas in Colorado, did a MapQuest, and the miles per gallon of the vehicle that would actually be transporting it across the country, and that's how I equated that. Also, I used professional estimates from Read and Read for what it would take to actually construct the site itself, the road predominantly, any blasting that would be needed, cranes that were needed, things of that nature. Man hours were something that I did not want to leave out. It's not part of the energy in to energy out, energy equilibrium summation, but it is something that is worth noting because these are humans that are devoting their time to this. But there is also consumption totaled up in this to give you a total energy in summation. Now on this slide, it is the energy production at the 80-meter hub height. And what I've done is I've used a formula that encompasses your power per wind speed, your swept area of the turbine itself, and then factoring in the wind speed, which is different than power per. In a colder area, it's less dense, or it's more dense air, so there's actually more power with that wind versus a warmer area. That's what rho is. These are balanced off of hours per month, so it is on a monthly basis, and also based on those University of Massachusetts Amherst studies, they broke down the wind speeds per month. So I have monthly averages. So everything is as close as I could get. If you do a yearly average, you'll actually get a lot different of an answer if you do monthly averages. So what did we do? Did we produce more than we consumed? And usually you are looking at a 20-year lifespan of a wind farm. That's considered the rough usability life of a turbine. There may be other things, gearboxes that needed to be changed out before that, other maintenance issues that need to be addressed before the 20-year lifespan, but by and large you're considering a wind farm to be useful for about 20 years. So for that, we found that yes, we have produced, when considering a 20-year lifespan of a farm, we have produced more than we consumed. We reached energy equilibrium at 4.9 years, leaving us roughly 16.1 years of energy surplus. And I actually have that equated into megawatt hours. Additional information, what could we power with that? I don't like that I have the census from 1997 for household energy consumption, but it was the only relevant information to my area and the area close proximity to where the farm would actually be. That was the most recent information that I could gather. So roughly we could supply for a year 4,344 average Maine households. It's better than nothing. So I briefly talk about Vestas and their life cycle analysis that they've performed a lot more in depth. What they also did was they had a scale of farm that was a lot larger than mine was. They had 100 turbines in a relatively flat area. So they reached energy equilibrium in 6.6 months. The difference being larger machines, more machines, flatter area, versus my project, which was less machines, smaller machines, in a lot more difficult area. Granted, I have better wind speeds here than they did for the majority of their studies, but things really start to make a lot more sense when you get to the last slide, which is thinking on it on a lot longer term basis versus a short term basis. When you're thinking of long term, you can actually get a lot more energy out because you could put turbines up in an existing site with existing roads and an existing data set. Understanding new technology as well will hopefully increase efficiency. So why was it that it took 4.9 years versus theirs 6.6 months? Like I stated before, less turbines, smaller turbines, more difficult of an area. And then here, talk again about long-term planning, which I think should be on the forethought of most urban development and rural development workers when you start thinking a lot more about the long-term good of our planet in general. So I thank you very much for viewing my site and for taking the time to view this video about my Ragged Mountain wind turbine project. I appreciate you viewing the site, and please feel free to email me if you have any questions, owencasas@gmail.com. Have a great day.